AP Chemistry, Screencast 2.9, Combustion Analysis. This is something you probably didn't do in first-year chemistry, but it's a classic way of identifying an unknown substance. You burn it, and then use the masses of the products that you formed to figure out the empirical formula by a back calculation of what you must have started with. Given enough information, you could then get a molecular formula, which then, if you're lucky, can give you a chemical structure, although you have to watch out for isomers, which are different substances that have the same molecular formula. Okay, so here's a sample problem. The anabolic steroid dianabol, which is a substance that Arnold Schwarzenegger admitted to the long-term use of, it consists of carbon, hydrogen, and oxygen. Its molecular mass is 300.44 grams per mole. If you take 14.765 grams of pure dianabol and burn it, you'll get about 43 grams of carbon dioxide and 12.5 roughly grams of water. From that we can figure out the molecular formula of dianabol. What we'll do is we'll find out how many grams of carbon, hydrogen, and oxygen are in dianabol, and we'll get our molar masses, right? So we started with 43.257 grams of carbon dioxide, which is close to a mole. But anytime we take a mole of that carbon dioxide, it contains 1 mole of carbon, does it not? In other words, it's about 12/44 carbon. And the carbon has a mass of 12 grams, so that carbon dioxide has 11.85 grams of carbon. That's almost a mole, isn't it? And we'll do similarly for the water, right? We have 12.395 grams of water. 18 grams is a mole. Every mole of water, however, has 2 moles of hydrogen. Therefore, those 12.395 grams of hydrogen has 1.387 grams of that. 12.395 grams of water has 1.4 roughly grams of hydrogen. Fine. The rest is oxygen. Now let's see, we started with 14.765. We could go ahead and do the same calculation, but let's save some time and say that the rest, which is 1.573 grams, is oxygen. So that's the gram amounts of carbon, hydrogen, oxygen that must be present in dianabol, right? Let's get an empirical formula. This is, we have to convert each one to moles, right? That is just about a mole of carbon. Hydrogen, it looks like about 1.4 moles of hydrogen, since 1 gram is a mole. And oxygen, it's 1.5/16 moles of oxygen. Resist the urge to go O2 here, because we're simply talking about O. We're not dealing with O2 molecules, or how many oxygen atoms, essentially, are there. And that right there is our mole ratio. Now you could have tacked it on right here, but you'll see that when you do it in this process, it saves you a step because we had to go back to grams anyhow in a second. So let's go ahead and take a look. This means we have C subscript 0.983, H subscript 0.376, O subscript 0.0983. That's the way I usually write it because it is the ratio. But we need whole numbers. The secret at this point is to divide by the smallest guy, which is clearly oxygen. That will by definition make it 1, and hopefully will give you either whole numbers for the other ones or half, occasionally a third. Let's see what we get when we divide each one by the little guy. 10 of these, 14 of those, and 1 of those. Ooh, all whole numbers. So C10H14O is our empirical formula. Nice. Does that match the molecular formula? Well, the molecular weight is 150.22 grams based on that ratio, but it's supposed to be 300.44. Can you not see that we have to scale by a factor of 2? Dianabol must in fact be C20H28O2. Now there it is mathematically. I never do it that way. I just recognize that you got to double it to get there, and there you go, 150.22 grams per mole, and that's the answer of the problem. You know, looking at this, I don't know why we didn't bother and just throwing in your mole ratios right here and do it all in one step. But in any event, that is the molecular formula dianabol, which happens to fit that chemical structure right there. If you're an organic chemist, there's your steroid. dianabol, and that's how you do a combustion analysis type problem. These do require some practice. I recommend that you do a bunch of these.